Welcome to Elevate Learn. In this tutorial, we're diving into two powerful Python features that professional developers use every single day: abstract base classes and protocols. If you've ever found yourself wishing you could force subclasses to implement certain methods, or you've struggled to define flexible interfaces that work across your project, this is exactly what you need. By the end of this video, you'll understand how to write cleaner, more maintainable code that scales beautifully. Let's get started. Here's the roadmap for our journey today. We'll start with the fundamentals of abstract base classes, understanding what they are and why they matter in your Python projects. Then we'll explore how to implement abstract methods and properties to enforce contracts. Next, we'll introduce protocols, Python's elegant approach to structural typing that gives you even more flexibility. Throughout the lesson, you'll see real-world examples you can use immediately. We'll compare when to use ABCs versus protocols, highlight common mistakes developers make, and finish with a quick knowledge check to cement your understanding. By the time we're done, you'll be equipped to architect better solutions. Abstract base classes, or ABCs, are like a contract in software design. Imagine you're leading a team building payment processors. You want every payment processor, whether it handles credit cards, crypto, or PayPal, to implement specific methods like process and validate. ABCs let you define exactly what those methods must be, and Python will refuse to create an instance of any payment processor that forgets to implement them. This prevents runtime errors and ensures consistency. It's one of Python's most elegant features for enforcing architectural decisions across large code bases. When you use ABCs correctly, you're essentially saying, any subclass of payment processor must implement these methods, or you'll get an error immediately. Now let's talk about the mechanics. The @abstract method decorator is your enforcement tool. When you mark a method as abstract, Python's ABC module prevents anyone from instantiating your class until all abstract methods are implemented in a subclass. You can also create abstract properties using a combination of @property and @abstract method, which is powerful for enforcing that subclasses provide certain attributes. A cool feature: abstract methods can have actual implementations. Subclasses override them, but they can call the parent's version using super, giving you flexibility to provide default behavior while still forcing the override. This is perfect for situations where you want to guarantee a method exists but allow the parent class to provide a helpful starting point. Protocols are a more recent addition to Python, introduced with the typing module in Python 3.8. They're fascinating because they flip the inheritance requirement on its head. Instead of saying you must inherit from my ABC, protocols say, if you have these methods, you're good. This is structural subtyping, and it's incredibly powerful for working with code you don't control. For example, if you want to work with any object that has a read and write method, you can define a protocol for it, and any existing class, even one written before your protocol existed, automatically qualifies. You can even make protocols runtime checkable, so isInstance and other runtime checks work perfectly. Protocols are lighter weight than ABCs and give you incredible flexibility in real-world code bases. Let's build something real. Here we're creating a payment processing system using abstract base classes. Our payment processor ABC defines two abstract methods: process and validate. Any class inheriting from it must implement both. Notice we also have a concrete method, log_transaction, that subclasses inherit. Then we create two concrete implementations: credit card processor and crypto processor. Each implements the abstract methods in their own way. The beauty here is that we can treat all processors uniformly. As long as they're payment processors, we know they'll have those methods. Try instantiating payment processor directly, and you'll get a type error. That's the magic of ABCs. They enforce architectural decisions automatically. This pattern scales beautifully to large systems with many different processors. Look at that output. Our payment system is working perfectly. The credit card processor and crypto processor both instantiate successfully because they implement the abstract methods. When we loop through our processors, each one processes the payment in its own way, one via card, one via blockchain. The log_transaction method, inherited from the ABC, runs in both cases, showing how concrete methods in an ABC provide shared functionality. Try removing the validate method from either processor and run this code. you'll immediately get a type error saying the abstract method isn't implemented. That's exactly what we want. Immediate feedback that something's wrong, rather than mysterious failures hours later in production. Now let's explore protocols with a real-world serialization example. Notice that user and product don't inherit from anything. They're completely independent classes. But we define a protocol called serializer that says, any object with a serialized method is considered a serializer. We mark it with at runtime_checkable, which lets us use IceInstance. Now here's the magic. Without any explicit inheritance, user and product are already serializers because they have the serialized method. In save_object, we check IceInstance and it works perfectly. This is incredibly powerful because you can write protocols for existing third-party code, and those classes automatically satisfy the protocol. You don't need to modify them or even have them import your protocol. Protocols are about what objects do, not who their parents are. Beautiful. Both user and product are recognized as serializers, even though they never explicitly inherited from anything. Our save_object function treats them uniformly because they both satisfy the protocol. They both have a serialized method that returns a string. This is the power of structural subtyping. If you had legacy code with 1,000 classes that already had serialized methods, you could wrap them with a protocol today, and all of them would suddenly qualify without any code changes. This is why protocols are so valuable in real-world Python. They work with existing codebases, third-party libraries, and code you didn't write. Notice the IceInstance check works because we used at runtime_checkable. Without it, the protocol would only be useful for static type checking, not runtime validation. Let's level up with more advanced ABC features. Here we're creating a datastore abstract base class that enforces two things. Subclasses must provide a connection_string property, and they must implement the connect and query methods. Notice that the connect method has a default implementation that includes logging. When PostgreStore implements it, it calls super.connect to get that default behavior, then adds its own. This is powerful. You can provide sensible defaults in your ABC that subclasses build upon. The connection_string property is abstract, meaning every subclass must define it. This ensures the logging in connect always has what it needs. In PostgreStore, we implement the property to return the appropriate connection string. This pattern scales beautifully. You can have 10 different databases all providing their own connection strings and connect implementations, but they all go through the same logging mechanism. Perfect. The PostgreStore successfully implements the abstract contract. We see the default logging message from datastore.connect, followed by the Postgre-specific message. The connection_string property is accessed within connect, proving that the abstract property requirement works as intended. The query method returns data. This architecture is powerful because you could add MySQL store, Mongo store, or Redis store, each with its own connect and query logic, but they'd all follow the same contract. The ABC ensures consistency while allowing flexibility. If someone forgets to implement query in a new subclass, they'll get an immediate error rather than discovering it at runtime when someone tries to call query on it. Here's a beautiful real-world example, a plugin system for loggers. We define loghandler as an ABC with one abstract method, handle. Any logger, console logger, file logger, future email logger, Slack logger must implement it. The application doesn't care what loggers it receives, as long as they're log handlers. This is how frameworks stay stable while being infinitely extensible. Third-party developers can create custom loggers without modifying your code. When you pass a list of different loggers to application, it treats them all uniformly. Each logger does its own thing, console outputs text, file writes to disk, but application doesn't need to know or care. This is the power of well-designed ABCs. They create stable contracts that enable others to build on your framework. Now let's clarify when to use each. Protocols and ABCs solve different problems. ABCs are about enforcement and inheritance. You must inherit from me and implement my abstract methods. Use ABCs when you're building a framework where you control the inheritance hierarchy and need guarantee that subclasses implement specific methods. Protocols are about compatibility and structure. If you have these methods, you're compatible with me. Use protocols when you want to work with code that doesn't inherit from you, like third-party libraries or legacy code. If you're integrating a new analytics provider and want to guarantee it has send_event and flush methods, a protocol is perfect because the analytics provider probably doesn't know your protocol exists. If you're building an app framework where plugins must implement setup, run, and tear down methods, use an ABC because you control the hierarchy and want runtime enforcement. In practice, teams often use both ABCs for their own code and protocols for integration with external systems. Let me point out some common mistakes I see in real code bases. First, people mark methods as abstract without using the @abstract method decorator, just writing pass and hoping subclasses override it. That doesn't work. Python won't enforce anything without the decorator. Second, developers sometimes make every single method abstract, creating brittle hierarchies that are hard to use and extend. The sweet spot is strategic. Abstract the methods that define your contract, keep the rest concrete to provide shared functionality. Third, forgetting to import ABC from the ABC module, or not inheriting from ABC. These create silent failures rather than clear errors. Fourth, misunderstanding protocols and using them when you should use ABCs. Remember, ABCs are inheritance-based, protocols are structural. Use the right tool for the problem. Finally, don't over-engineer early. Start simple, add ABCs and protocols when you see the need for contracts across your codebase. Quick question for you. What happens if you try to create an instance of an ABC that still has unimplemented abstract methods? The answer is Python raises a type error right away. This is the whole point of ABCs. They catch mistakes instantly rather than letting broken code slip into production. The error message is clear and helpful, telling you exactly which abstract methods are missing. This fail-fast behavior saves you hours of debugging compared to silently allowing the instantiation and discovering the missing method when someone actually calls it. It's one of Python's best features for preventing bugs. Here's another key question. Can a class satisfy a protocol without explicitly inheriting from it? The answer is yes. That's the entire point of protocols. They work with structural subtyping. If a class has all the methods and properties the protocol requires, it automatically satisfies the protocol. You don't even need to import the protocol in that class. This is incredibly powerful for working with code you don't control. A third-party library's logging class might accidentally satisfy your log handler protocol without anyone ever writing inheritance code. In practice, you might add @runtime_checkable to enable isInstance checks, but the protocol works whether or not you use that decorator. One more important distinction. Which approach lets subclasses call the parent implementation using super? That's ABCs only. Because ABCs use real inheritance, subclasses can call super to access the parent's implementation and then extend it. Protocols don't support this because they're structural, there's no inheritance relationship. This is another reason to choose ABCs when you want to provide default implementations that subclasses enhance. If you don't need that shared behavior, protocols offer flexibility. But if you want to say, here's a sensible default implementation that everyone inherits, but you can override and enhance it, ABCs are your tool. Congratulations! You've just leveled up your Python architecture skills. Let's lock in the key takeaways. Use abstract base classes when you're building frameworks, libraries, or systems where you control the inheritance hierarchy and need to guarantee implementations. Use @abstract method to prevent incomplete implementations. This fails fast and saves you hours of debugging. Mix abstract and concrete methods strategically. Abstract the critical contract, concrete everything else. Use protocols when you want flexibility, when you're integrating with third-party code, or when you need structural typing without inheritance. Remember @runtime_checkable for isInstance checks with protocols. Both ABCs and protocols are essential tools in professional Python development. The choice between them depends on your specific problem. Enforcement and inheritance hierarchy, ABCs, or flexibility and structure, protocols. The code you write today, informed by these patterns, will be easier to test, extend, and maintain for years to come. Keep practicing, and you'll develop an intuition for when each tool is right. Thanks for learning with Elevate Learn.